Okay, let's start. Do you have any questions? All good? All right. So we'll be, okay, fine. So first of all, right, we're finished with calculus. I mean, finished in quote, meaning, the basics were covered, right? And, it's a vast area, so you can't really, right, technically exhaust it. We'll probably see it here and there as we continue with the course, but the majority, right, which is the idea of the Ito integral and the Ito's formula, right? Integration and differentiation have been conveyed to you. Okay, so now where are we, right? And where we're going next. So basically, we spent a little bit of time covering stochastic calculus, right? And its kind of subtlety to, in some way, right, explain how these three formulas, these three expression rather, are equivalent, right? So these three are equivalent, right? Using Ito's formula, one way or another. So now let us discuss, right, the next step, which is the risk-neutral pricing framework. So there are two aspects here that I want to discuss. First one is kind of important, but I find it's not discussed in a lot of places, which is what is risk neutral, okay? What is risk neutral pricing? Again, I mean, it's basically the framework that we use all the time, right? So we better have some understanding of what we're doing. And second is the change of measure, right? In Black-Scholes framework, or rather with respect to Brownian motion. And the big name for it, if you want, is the so-called Gassano theorem. Again, I mean, we'll talk about the techniques. The theorem I won't state in its full details. It's something like, covered here anyway. All right, so let's start out with item one. So I believe that, right, all of you have done some risk neutral pricing, at least in Math Finance 1, etc. So what is risk neutral pricing, or what is risk neutral? Why do we do it? Can anyone explain to me what is risk neutral? What does it mean? So at least superficially, you might know something like this, that there are two formulations, right, of Black-Scholes model. One in this way, right? Here we say the drift is mu, and the other one, right, is this. Where the drift is R, right? And so this is the, physical, right, probability. This is a risk neutral, right? But why, right? What's the point? Why do we switch to this, right? Why do we switch to this when we do pricing? And, right, how do we do it, right? That's two, okay? So roughly speaking, right, a lot of times you kind of just use this, right? Funny enough, if you do pricing, you won't even remember this. But, right, if you don't understand the framework, again, right, I think you might run into some subtle issue here and there. Okay, so no one knows? I mean, or no one wants to say something?
Does it mean the return of the investment at least should be the R, the market or the client interest?
That's more like a general observation that basically when you are investing in a risky investment, then your average return, right, should be higher than the risk-free rate to reflect, the price of bearing risk. That's in some area, but it's not addressing, right, the question of what does risk neutral mean, right? I mean, you kind of actually addressing the idea of risk and how, we pay for risk, right? How we get rewarded for risk. But so it's somewhere there, but actually it doesn't get to the point of risk neutral, right? What does neutral mean? What are you being neutral about? Okay. Or actually, when I interviewed a long time ago with Moody, I think, the gentleman there asked me, why do we use risk neutral pricing? That's an interview question. And basically, I think he asked, do we need to use risk neutral pricing or why, I was saying something along the line of, oh, wow, you can have no arbitrage. And he was very unhappy. He said there's always arbitrage. And anyway, right, point is I flunked that interview. So they do bring up those kind of questions, right, on the interview, just so you know. I mean, I don't know, maybe once in a while, but all right. So so hopefully you won't flunk these kind of questions in the future. But let's start with a question, right? Here's a very easy question, but it's a fundamental question. Let's suppose we play a game, right, a lottery, where, right, you receive, right, $1,000, let's say with probability P, right? And you receive 0 with probability 1 minus P. Okay. Obviously, right, the question that we always ask is the price of the game or the price of this lottery, right? How much are you willing to pay for this game? And the answer is? Okay. Now, next question will be why?
This is the expected value.
Okay, so sure. But right, here's the question. So suppose, right, let's do so by saying this, you are claiming that you think this is a fair price, meaning that if I ask you to pay 1,000 P for this game, you will be okay, right? You'll be happy to play it. Is that what you're saying?
Technically, yes, but I guess because this is the expected value, so it means it doesn't necessarily mean you will get this value. It's just
no. So I'm right. So exactly, this is the question. When you claim this is the price, what are you saying? Are you saying that if I sell you this, you'll be happy to pay it? That's my question, right?
Yes.
All right. So we can do it right now because we have Python, right? Which is fair. So you know I won't cheat you. I'll be generous with you. I'll let P be 1%. So you only have to pay me $10, right? I will roll a number. If it's 1, then I'll pay you $1,000. I promise. Otherwise, you pay me $10. Shall we do it? You want to do it? I hope not, right? I mean, well, not hope. You could, just for the fun of it, if you're, $10 doesn't mean much to you, right? But notice that some of our students won't do that. Now, actually, if you want to be a little bit more dramatic, I'm a cheap guy. $1 is good enough for me for a coffee. How about that? Then I get $1 from you for free, right? Almost. So that's where, right, the question lies. So you see that, right? This is our knee-jerk answer. This is the answer you got taught in, probability courses. And I hope, right, in such courses, there is an explanation, right? The explanation is law of large number. What that means is this answer only makes sense if me and you repeat this game, let's say 1,000 times, right? Then actually it doesn't matter what P is. You and I will gain and lose on average that much. Agree? You understand what I'm trying to say? Right? So this is the basis of casino pricing. Yes? Casino gives you a slight disadvantage, like 0.49%, 49% of, winning the game. Okay, so it seems attractive in the short run, but in the long run, right, they will always pocket their money. On the other hand, right, notice that exactly this question, right, where P is in some certain range, begs a different kind of question. What if the game is only played once? Okay, so law of large number justifies this. But what if it only plays once? Or, a few times? And actually, this is more in the risk neutral, in the option pricing framework, right? Because you buy an option, you're not gonna keep repeating that option 1,000 times into the future. And even if you do, right, the market will change. So that's not gonna be the same thing. So in fact, right, the question of playing once, or actually, even in real life, right, you're not going to walk into a casino and sit there, and even if the game is fair, right, say 1,000 times, unless you're really, addicted, right? So playing a few times or playing once, the price of the game, right, that's a more relevant question, right? I mean, I'm not saying that the law of large number framework is not relevant, but it's not relevant in some contexts, right? Small sample sized, one-time game. Now, in that case, if you notice, right, the kind of the hesitation or the kind of unsureness that you were talking about displays exactly this question, risk preference. All right. So if you play the game once, the way we have to price it is based on your risk preference. In other words, right, when we go back to the 0.01 here, right? For some people, that's not an attractive game. If it's not attractive, you probably think that they're risk averse. And these are really technical names, right? If it's attractive to them, then they are risk seeking. And if it's, indifferent, right? They don't care one way or another, then they are risk neutral. Okay. We'll talk more about this because it's actually very, very interesting and important. So basically, first of all, right, I want you to understand that behind the act of pricing, and option pricing is one of them, right? You can just really think of it as a game. So literally option pricing is like gambling in some way. You are exchanging a guarantee payment with a random payment. That's literally always what's behind pricing, right? Because when I ask you to pay for a price, I ask you to give me a sure amount in exchange for a random amount. Okay. And so the amount that, so basically you're trading risk. Okay, that's what I'm trying to say. And so a risk-averse person, you can see, has some preference for the sure amount versus the random amount. The risk-seeking person, on the other hand, has more preference for the riskiness, for the random payment over the sure payment. And the risk-neutral person, right, again, doesn't care one way or another. Okay. Now, again, I guess this is in psychology, whatever, we probably are in this range more than in this, but we would know one or two of our friends, right, who are in this area. Okay, so now let me write something down real quick, and we'll discuss more details. Roughly speaking, you can, right, classify a person being in this area like this. If someone is risk averse, the value of the game for them is less than the expectation. If they are risk neutral, by the way, right, the price, okay. So we'll have a technical name for the price later on, but the price is called the certainty equivalence, okay, of the game, of the random payment. Meaning, right, the price is what anyone would feel is equivalent, you know, to the happiness, right? We'll get to that they get. So for the risk-averse person, right, the price, the certainty equivalence is less than that. For the risk-neutral, the price is equal. I might get the direction wrong. I think I'm okay here, but we'll see. For the risk-seeking person, the price, the value of the game is higher, okay, than expectation. Okay, we'll check this. All right. But so roughly you can see why, right? Because for a risk-averse person, right, the value of the game is not as high as the expectation. That's why they won't pay the expectation. Okay. For the risk-seeking person, they'll be happy to pay. But let's explore this some more, okay? And this has to do with, this actually has a connection with the notion of a utility function. All right, which you might learn in economics 101 and that kind of thing. It sounds like a, you know, a fancy notion that only economists use to argue some of those abstract ideas they use. It turns out it has some interesting application, right? So let's take a look. So basically, a utility function, it maps, you know, payment or money, kind of, to happiness, which is a weird thing, right? So that's where it's kind of a little bit funny, right? But well, let's just bear with it for a minute, right? Like I said, it does have its point. So basically, it tries to measure, right, a person's happiness with the amount of dollars they received, right? And so they like to be deep, right? Hopefully. So here's the payment, right? And here's happiness, right? And basically it's utility, right? Happiness is utility. They would argue that most people's utility function looks like this. All right. So the key word is, of course, it's a concave function. The reason, right, is that when you're, okay. So first of all, I think this is convention that when you have zero money, you have no happiness. But when you're poor, right, then one extra dollar means much more to you than when you're super rich, right? I think there's a joke that says Bill Gates won't right, stoop down and pick up a $5 bill or something because, you know, he makes much more than that by the time he pick up the money. Anyway, the point is, right, the utility function of a person usually looks like this. So, but we'll take a look, right? Basically, the other possibilities are also there. There's a convex shape and there's a straight shape, all right? And you might be a little bit suspicious that this concaveness is connected with risk aversion. So anyway, right? Now, how do we price? How do we formulate pricing? Okay, using utility function. Well, so the idea is this, right? You have a random payment. Yes, like this. Okay, will be our stock example. Now, so by the way, right? So let's call it phi. Okay, phi as our utility function. Then you have your happiness, right? P of x. That's the happiness you receive will be random, based on how much you received. We could take the average of this, first of all, right? So this will be the average happiness you receive from the game. Now notice that here's what they do start to make sense, but it's a little funny. First of all, notice this cannot be a price because it's in a unit of utility, right? It's in the unit of happiness. So how do you convert that to price? Well, you take the inverse. All right. This will be exactly what we call the certainty equivalence of the random payment, right? CE is certainty equivalence, like I said before. Or exactly, this is the price for that person. Okay. Now let's see why this at least makes sense. First of all, right, notice that this is in a unit of dollars, okay? This is certainty equivalence. This is in unit of dollars. So actually, it's say that the price the person is willing to pay is such that the happiness they receive, right, from that price is equal to the average happiness they receive from the game. Does that make sense? That's what certainty equivalence does, right? Because I mean, we assume that this utility function is one-to-one and onto, so it has an inverse, right? So when you map over here, right? So the happiness they receive paying that price is equal to the average happiness they receive from the game. From that point of view, right? This is a fair price. Is that okay? Now, so that's the proposed, right? Pricing using utility function. We'll discuss, the merit of it and things like that. But let's see how, right, this is connected to the risk averseness, that kind of thing, right? And the connection is via something called Jensen's inequality. Does anyone know what that is? What does it say?
I think it's like the function square less than the square of the function.
Okay, so it's something like this. First of all, it's not just that, but it's like that. So which direction?
The right one is larger.
Yes, right. And how do you know?
Because it's concave. Oh no, it's convex.
Right, right. But there's a way to look at that too. But here, right, it's basically the variance. So the variance must be positive. So at least that's a trick. I'm not trying to say it explains it, right? So, but it's a trick that says that if phi is convex, then expectation of phi of x is right. Agree? If phi is concave, then the opposite happens. And of course, right, if phi is linear, right? All right. So now coupled with this, I claim that, right? Exactly, you see that a person whose utility function is concave will be risk averse. And of course, right, why, right? What does that mean? So if we base it on my definition up here, which is probably is okay, right? Then I think what I'm trying to say is this, I need to show that the certainty equivalence of x will be less than or equal to expectation of x for that person. Okay? Do you agree? Because the certainty equivalence, right, is the price according to utility function. Okay, so far? So I mean, right, I hope equality here is okay here. So let's not bother with that. Okay, how do we check? Well, the certainty equivalence is what? Is the phi inverse of expectation of phi of x, right? Agree? Well, what does that mean? That means this, right? Is that true? Yes. Okay. Again, right, I just want to do the abstract math here a little bit to show you the connection. But do pay attention, right? This is not all abstract nonsense, right? Even though there's this kind of weird thing to go to the realm of the happiness, which we cannot measure. But the shape of the preference, right, is a real thing, right? It can be done with psychology. And also, right, this idea here, actually, if you want, doesn't appeal to any kind of utility function. I just want to show you the connection, all right? It's really something that makes sense. And so, right, I hope with the same argument, you can see now that convex, right, will corresponds to risk-seeking and linear, right, will corresponds to risk-neutral. All right. And so we'll explain some more here. I hope that explains why, at least you see why, this claim of price equals to expectation seems to stand. We'll explain some more, but let's go back to my interview question. Basically, the answer the guy was looking for is it's not about no arbitrage kind of thing, even though I still believe that's the right answer for the guys on the academic side. For the practitioner side, the answer he gave was because we cannot measure, or we don't want to waste time model a customer's utility function. So the easiest thing you want to assume is that person's risk neutral and just go with the pricing. That's literally the answer he gave. That, right? Basically, you see that if you can price, if you know the person's utility function, then you can definitely come up with a precise price like this. But I guess, I don't know. Again, you can make up a story here, but I think what goes on in his mind is, or people's mind is, you don't want to spend time modeling each customer utility function, because then, right, each one of them will have a different utility function. A universal assumption would be then, let's assume everyone is risk neutral, okay? And then use that to price. Again, I'm not trying to say that that's super convincing, at least it's something, right? And or at least you should be aware of where risk neutral pricing comes from. It's kind of the refusal or the being agnostic about the utility function. You just don't model the utility function, right? You say that, let me assume everyone's risk neutral. Now there's another better way to explain it. I'm gonna say it down here, right? But somewhere along the line, that's still the case, that basically you don't model the utility function. Or you assume that people are generally risk neutral, all right? So that's one. And by the way, so I want you to be aware that risk neutral does go back to this, which seems suspiciously dangerously close to the law of large number. It's not the same concept, all right? It's not the same concept. All right, so now let us do some more, right? And this is just a picture representation of the above, which hopefully will help. So let's take a look at this, right, and the utility function. So let's take our typical risk neutral, risk averse customer. So, right, X is going to be 1,000 with probability P, 0, probability 1 minus P. All right, so expectation of X, right, is somewhere let me draw it a little bit below here, right? So how do I want to say this? So basically, right, you have a straight line, right? What is this straight line? This straight line maps the expected so this is basically what do I want to say here? So here's 1,000. Right, just give me a moment here. If it's 1,000, right, so this is a utility at 1,000. This line, yeah. So how to say this, right? So I want to say is if P equals to 1, right? Then of course this is 1,000, so this is this, right? But if P is not equal to 1, then it's going to be somewhere in between. Gosh, I lose my track, but okay, let's just go back and see what we have. So there's a straight line, okay? I think the straight line has a meaning. I lose my thought a little bit, but let's just say that, right? In general, right, 1,000 P is somewhere here, right? 1,000 P is somewhere here. Now, if you were, right, if you were to receive this 1,000 P guarantee, right, for this person, then their happiness is up here, right? This is the happiness they would receive if they were to receive 1,000 P directly. I want to say that the intersection here is exactly, yeah, it should make sense, right? This is exactly the happiness they would receive from this random payment. Is that true? What I'm trying to say is the happiness they would receive is lower. I want to claim that this line is exactly the expected utility. No, right? That's not true. Because expected utility is P times a fee of 1,000. That's not 1,000 P. P times fee of 1,000. Oh yeah, that's true, right? expected utility, right, is P times phi of 1,000. Do you agree? So this is P of 1,000, right? And then when P equal to 0 is 0. So this line is exactly the line of expected utility, right? Am I okay? Because, right, expected utility as a function of P, you see? So I want to write the expected utility as a function of P. Will be P times phi 1,000. Do you agree? So when P equal to 0 is 0. When P equals to 1 is phi of 1,000. And this is a straight line. So it's this line right here. Agree? So if you travel along this line, right, you will get the expected utility as a function of P. So for example, right, when P equals to something less than 1, right, then this is the expected utility, while this is the actual utility. If you were to receive this quantity for sure. And that's why, right, this person will prefer to receive this quantity rather than receive this quantity as an expected, as a random amount. You understand? So so again, right, this is just trying to say again, this is phi of expectation of x. So it's showing you again the phi of expectation of x is less than or equal to expectation of phi of, higher, right? Higher. That's why you prefer this. You prefer to have a certain amount over the random amount, right? Oh, wait, am I right? I'm confusing myself here. Sorry. Am I saying it right? Phi of expectation of x. Yep, that's true. And then, oh, sorry, this is expectation of phi of x, expected utility. Right, this is expected utility. All right, so what do I want to say, right? So on the other hand, there's another way you can see it like this. Another way you can see it like this is this, that, right, if you were to receive this amount, right, if you were to receive this amount, then the point, right, that you would be happy that has the same, right, that has the same utility compared to this guy, expected utility, is this point right here. Right, this point right here, this amount, right, will have the same utility as the expected utility here for this quantity. So this is exactly the certainty equivalence of this game, right? Because at this point, the utility is equal to the expected utility that you receive. And so you see the certainty equivalence is lower, right, than the price, than the expected utility, than the expected payment, right? So another way to see it is the certainty equivalence is less than the expected payment. All right, so again, two ways you can see it, that the utility of the for sure payment is higher than the expected utility, or the certainty equivalence is less than the expected payment, right? It says the same thing. Now, finally, right, I want to point out that the gap here is what people will call the risk premium. Okay. is exactly what you must pay that person, right, to play this game in some way. So basically, this is exactly how much they would want to be compensated to forego a for sure payment to adopt a random payment. So that's the risk premium. Okay. So yeah, it's a graphical representation of exactly what we say above. All right. So yeah, I think what I said here, all of these are correct. It's just the concept's a little bit confusing, but do try to straighten all these things out, right? This line is expected utility, right? From an expected utility, you go horizontally, you get the certainty equivalence, and the gap is called the risk premium. All right, so yeah, questions, comments? All right, so the next thing I want to say is a piece of psychology, I think. They say that actually most people's utility function looks like this, where it actually has two sides. There's a side for gain and there's a side for loss. So what it's saying makes a lot of sense. When it comes to gain, people tend to be risk averse, meaning that people would prefer a guarantee payment over a random payment. On the other hand, when it comes to loss, most people are risk seeking, but you have to read it right. What it means is that people would prefer a random loss versus a guarantee loss. In other words, right, it can also make sense if you have faced a chance of losing $1,000 with probability 0.01 versus losing $10 for sure, you probably would prefer losing $1,000 with probability 0.01. Okay. Finally, there's a region here close to zero where people are risk neutral. So as long as you stay close to the zero range where, you know, payments are not so high and so low, you could assume that people are acting in a risk neutral manner. Okay. And so I guess this will give one last, right, justification for that risk neutral assumption that we used in pricing. Okay. So that's what I want to say about the risk neutral pricing framework. Any question?
I have a question.
Yep.
About why in the industry people use risk neutral model, because you said that the majority of us is risk averse. Why not just use, you know, a risk averse utility function to kind of model the pricing?
Yeah. So actually, there are a lot of research, right? Papers that literally use risk, you know, use this kind of pricing scheme. So first of all, right, utility function is a highly individualized notion. You and I would definitely have different utility function. Industry is about mass application, right? You cannot, first of all, because that really implies individual pricing. Yes, so that's one thing. Do you know what I'm trying to say? And that actually that's what the interview that I went with, I think that's what his assumption is. That you don't want to waste your effort modeling each person's individual preference, right? So that's really the implication. Now, that doesn't say that if you have a single client and you want to spend all your resource capturing his psychology, then you could come up with a better pricing for that individual, right? And definitely there are research paper in economics, in even math finance that does use this scheme. So you're right? But when you think of practical application, right? Definitely you don't even ask me to look at someone's utility function, right? Even in terms of computation, this is not a nasty piece of thing to do, right? So I'm trying to explain it. It's a nice theory to have, and it's a nice psychology to capture people's stuff, right? But I think if you want to do the actual math with it, it's super painful. And so I think it can be used to explain some qualitative behavior, right? Like people prefer this over that, like comparison. Well, you want to do actual numerical stuff, like this is the exact number that you should charge, then that becomes questionable. Does that make sense? And plus, right, I find this argument very convincing that the range around 0 is tend to be risk neutral. So we have some error, right? And actually, then the question is, how large is this region? But if you extend that to $100 or so, right? Which I guess most adults, right? Within the $100, they don't care so much. Who knows? Then you could assume risk neutral without much error. So I would say, right? But I agree that at the end of the day, right? This question, this notion of utility function is a very hard notion to capture. Yeah. Oh, and if you're interested, you can really look into this literature. They even model with different shape, like e to the 1 over lambda x, whatever, lambda is a coefficient, blah, blah, blah. You can play with it. They really do research on that. All right. Any other question? Yeah, I mean, like with some particular fee, like the exponential, you can really invert it and get the price. But again, right? One would question how real is that kind of thing. All right, so now let us now go back to our Black-Scholes framework, right? So in our Black-Scholes framework, first of all, right? Oh, I want to say one more thing, right? Now, so let's see how this risk neutral observation, right, applies to our pricing, right? So first of all, you do see that, right, from the point of view of above, then pricing is really, right, giving a price to a random payment, because this is a random payment, right? So actually, the question of pricing for us is, what is the fair price of a random payment, which is this, right? Because you are given this payment in the future, you discount to bring it back to the present. That doesn't negate the randomness, right? So what is the random payment here? What is the price of this random payment here, right? You are receiving this random payment when you enter a option, when you enter a contract. Do you agree? Now, of course, right, this hides one more fact, which is the randomness of the discount factor, right? I mean, discount factor is not always random, not always constant, right? It can be random, but for now, right, let's say that the source of randomness is only on this stock, right? But all in all, right, when you buy an option, you are due for a random payment. Okay, and so your question is, what's the price? And so, right, notice that again, if you really love the utility framework, right, then exactly the price is this, right, the certainty equivalence. Which, right, notice that it doesn't give much, but that's the price. Wait, did I do it right? Yeah, no, phi outside, right? Phi is not linear, so phi is this. Okay. Now, but right, one thing is this, that we know something more in terms of this pricing than just a pure utility function. One thing this must satisfy. What is it? So unlike, unlike like a game like the above, right? unlike the game like above, there's one more thing that we know must hold. The difference, right? So first of all, what I want to say is option pricing is like a random game pricing. So it's like gambling. But one more thing that makes it different though, and probably why people love trading more than gambling, is that there's a market. Okay, there's a market for it. This market makes some difference in this pricing scheme, because you think about it, right? In your casino or when you play a game, this is the only guy you can play a game with. But suppose there are tons of guys around here that keep selling the same game, and there must be some interaction along the line. And the interaction is this, very simple. When, oh God, I'm doing something very silly, right? I use fee as the value of the option, and I also use fee as the utility function. That's so stupid. Hold on. Let me do something like this. Let me just try call option, all right? But you know that this can be anything, all right? It doesn't have to be call option. All right, so this is the random payment I'm talking about. And so you apply utility function to that random payment, all right? Like that, okay? So what I'm trying to say is, wait, hold on, how many brackets do I have? 1, 2, 3, 4, yeah. What I'm trying to say is, right? So basically any function of x, any function, right, of st, you can chuck it into here and use this pricing framework. But one thing this must, and generally you don't know what this is. But there's one thing this must satisfy is when this guy is a identity function. When this guy is the identity function, in other words, right, using the utility framework, if you want, then this will be equal to, or this must be equal to, or must this be equal to? This must be equal to S0. And this has nothing to do with utility. This has to do with no arbitrage. And by the way, this is not the no arbitrage in the market. Sometimes say there must exist, but this is a no arbitrage in the very real sense of it. Because what are we saying here? This is the price you would pay to get a stock, right, in the future, right? Meaning that you are paying some amount for one share of Google in a month from now. Remember we asked this question before, right? It doesn't matter if stock of Google goes up or down, right? You will pay exactly what the current market price for that future share, right? You'll be crazy if you pay more or less. Of course, this assumes a liquidity, right, of the Google share, meaning that you must have access to Google share, right? If Google is illiquid, then of course someone may pay more, right, for the illiquidity. But if we assume perfect liquidity, then no one would be crazy to pay more, right, or less for Google price, for Google stock for one share in the future. Does it make sense? That's interesting because this is independent of utility function. It doesn't matter if the guy is risk-seeking, risk-neutral, or risk-averse. This equation must hold. So what actually that assumes is that guy's not crazy, meaning he's a rational person. So that's a different kind of thing, right? The rational consumer will always pay this for the future. So that's because of the market, right? That's because of the market. Has nothing to do with utility, all right? So there you go. So in fact, I mean, you could say still that, you know, a guy who, so basically then a guy who's risk-seeking might feel he's getting a deal. So that guy, probably you can say something like the guy who's risk-seeking will prefer to buy stock because somehow they feel this quality is higher, whatever, right? But what we're saying is like, you know, there is a line that ties these two together by the no arbitrage condition, irrespective of what this must be. Does that make sense? So that also goes back to what you were saying about risk neutral too. That somehow, right, when it comes to this kind of pricing, the market somehow enforce a certain kind of condition that is independent of utility function, right? So, all right. So now, right? Let's go with our risk neutral, right? Utility assumption. So now you know what that is now. So let's assume that we have a risk neutral guy, right? Let's assume we have a risk neutral guy. Then by that assumption, right, the guy must like this price, right? For the future stock price, which is this. Okay. And now here's where your math comes in, right? Because you have to do calculation at some point. What is this answer? What is this expectation? What is this expectation? Well, the only randomness is this, right? If you take the expectation of this, it will cancel out with that, leaving you with right? Oh, sorry, mu minus R. Yes. And now back to what Jingmei was saying, right? That mu is generally bigger than R. We can all see that. So definitely this is not S0. Okay. So maybe let me modify this a little bit. Maybe this is not a forcing assumption. But what I want to say is this, that any person, any rational customer must pay S0, right, for Vt equal to St regardless of fee. So maybe I don't know what this is, but regardless of what their preference is, they would agree that the price for St is S0, right, out of an independent assumption. Let me just say that. So they may have a secret, right, preference behind the scene, but transaction-wise, they cannot deviate from this market condition. So see, like that guy who flunked me for my interview may did it unfairly. maybe there's a no arbitrage assumption somewhere here, right? Because you see, right, for this argument, right, actually now that I think about it, right, the guy might still like to gamble. That doesn't change this equation, right? It may still be higher than S0. He might still like to buy stock. Yes, you know people like that. There are people who would like to buy crypto, right? Who buys Bitcoin, that kind of thing. So maybe, right, the rationale is because they like, right, the riskiness of it rather than the price itself, because the price just seems fair. Anyway, right, so the point is this now, that under the risk neutral assumption, it doesn't come out right. Yes, so something must be wrong. Our argument about no arbitrageness, right, is not wrong. So what's wrong is the model. What that means is, right, and you know this already, that this model is not how a risk neutral person would see the stock. Okay, this model means that this is not how a risk neutral person would see the stock. Okay, so a risk neutral person would not view, right, the stock as okay. But how would they view it like? Well, we kind of know, right, that basically, so first of all, let's just do some magic. Suppose you add R, right, and subtract R. So you have something like this. Okay, like that. Now notice, right, I'm not doing anything, I'm not changing anything in terms of the stock. I'm just adding and subtracting, right, the term R, right, divided by sigma because it cancels, right? So the stock is still the stock. But if somehow the person can view, so what do I mean by view, right? Now view will be adopting a probabilistic framework for the world, right? Meaning that, this goes into some other view of probability where basically probability is how you believe certain things happen with certain likelihood, okay? So if the person somehow can view this guy as a Brownian motion under some probability measure P tilde, then P tilde is our risk neutral probability. Meaning, right, that it reflects two things. It reflects the risk neutral pricing framework, meaning the price is the expectation, but moreover, is consistent with the no arbitrage condition. Does that make sense? So, right, there are a few things that we need to pay attention to here, right? Again, you want to still stay with the risk neutral, meaning that the person will view, right, the price, the payment as equal to expectation. But on the other hand, because of the no arbitrage condition, right, any rational customer must pay this much. Tying this together means that this person must adopt some point of view that allows this to happen. Is that okay? What I want to say is this, right? That a lot of times students make mistake of, right, thinking that when you jump from physical to risk neutral, it's like you abandon the world and you do something else. That's not true. The stock still so basically the stock still move in the same line. Whether or not you go, the stock is still the stock. What you change view is how likely the stock will move up and down. Understand? For example, right, when you roll a die or you toss a coin, right? When you change your point of view, that doesn't mean that suddenly the coin has three possibilities. The coin still has two possibilities. What you change the point of view is how likely head and tail will come up. So the physicalness of the object doesn't change. Therefore, right, there must be a connection between the Brownian motion here and the Brownian motion here. And the connection is this. All right. It's not like you completely grab something out in the thin air and slap it in. It might feel that way, right, in calculation. But physically, this is the same object. Therefore, there's a task somewhere to somehow convert this to a Brownian motion. All right. Because, right, if you just say that cheaply, right, cheaply, I just want this, then why not just arrive at that with a new Brownian motion? Okay, because right, some people would, and there will be, I'll say something in the next lecture maybe. There is some people would feel that there is a disconnect between the physical world and the risk neutral world, which is true, right? There is a disconnect, but the disconnect is from the probabilistic viewpoint, meaning that, Cyrus would view the coin as fair and I view the coin as unfair. That's the disconnection. The disconnection is not about Cyrus see the coin as having three possibilities and I see it too. No, right? That's not the disconnection. Okay. All right. What else? There's more connection than that. The connection is that even though the person adopts a new point of view, they cannot go too far from the original point of view. This is actually a technical term in math, equivalent. Equivalent means that the impossible event in both worlds are the same. All right. So even though you might view the likelihood as different, if something is impossible in one world, it must be impossible in the other world. Or equivalently, if something is guaranteed in one world, it must be guaranteed in the other world. Why, right? Again, if that's not true, then you can slip in some possibility that has zero probability in one world, but has positive probability in the other world. Then you actually do change, right, the physicality in some way. All right, so that's another connection. One more thing, right? This actually has a term. What is it called? Right, this term that we add to the Brownian motion, right, when we go from physical to risk neutral and vice versa. What is it called? It's a very famous term, Sharpe ratio. Also called the risk premium, market price of risk. All right. And I do believe that somewhere along the line is connected to the risk premium that we discussed up here. It has that connection. All right. I haven't really thought about it, but I think there's some connection. But anyway, straightforwardly, I hope you see the connection, right? Basically, this is the extra return one gets for investing in the stock, averaged by how many units of risk one has to pay for that, riskiness, right? Basically, this is very mundane. People make a big deal out of it. If you know stats, right? This is basically how many units of standard deviation that mu's above are, which makes sense, right? You measure performance by unit of standard deviation rather than, because for example, right, if you measure something in the unit of currency that's very inflated, then the guy might perform 10,000 units a day, but that doesn't mean anything, right? So anyway, actually, this is not true. That's not about currency. It's really about you really have to average out for the risk that you bear. Basically, if you gain 5%, but you have to bear a lot of risk for that, then that's not worth as much. Yeah, I didn't say it right. Anyway, right, so that's the story for the risk neutral framework. Right, so that's actually point one that we set out to talk about. There, all right. Now let's talk about point two, which is how it's actually done. So change of measure. So here, this is the one place where filtration will need to be dragged in a little bit. So there is a filtration, right, that we talked about. Not we talked about, but we know that's implicitly behind the scene, right? Keeps track of information, right, from time 0 to time t. And this I will rely on Professor Larson, right, teaching. But basically, right, the idea is as you go up in time, right, you get more information, right? The filtration gets larger. And each of them is just a sigma algebra, right? Each of them is a sigma algebra, meaning a collection of events. So the more you go up in time, right, the more events you have. And so when you define a probability, right, a probability is defined on event, right, on events. So to define the probability on a sigma algebra, you will technically just need to define it on the largest sigma algebra, because right by implication you will define it everywhere else. Okay. So now, right, so when you want to change measure, right, when you want to define a new one, you also only need to define it on the biggest filtration, because everything else will be implied. Now, how do you define a change of measure? You would need to something called a change of measure kernel. Basically, that's a fancy term for a random variable. That's in the biggest sigma algebra. It needs to satisfy two properties. So by the way, right, the direction is we will change from p to p tilde, all right? Pay attention. It will get confusing because you don't know which one. The other direction is just the inverse of it, but you know. You need this to satisfy two things. This random variable must be positive, and its average, its mean is 1. Why do you need this? The reason is then for any random variable, right, this will be the definition. Okay. So this is the definition of the change of probability, change of measure. So you understand what this means, right? First of all, right, this implies probability, right? Because expectation implies probability, right? You know, if you want a probability of an event, right? Of E as an event, then you just do it with a indicator function, right? And then you go, right? So I want to say that the expectation of a random variable is more general than defining a probability. All right. Okay, so far. So maybe, I'm not sure if this is a little bit abstract, but let me give you an example. And the example is actually the one that we will use. So ZT, right, will be this one. Oh, sorry, minus. All right. So notice it's very funny, there's a minus here. But first of all, right, notice why ZT must be positive. The reason is if ZT is not positive, right? So for example, what's an event that you care about? For example, let's say event E is WT being positive, right? Then what's the probability of E in the original probability? P is, what's P? If maybe E is a weird, right? Maybe I'll say A as an event. What's probability of A? One half, right? Because it's a random motion. Now, what do you think P tilde of A is? Well, better not be 1/2, right? Otherwise, I did not change measure. Well, by definition, that will be E tilde of indicator function of A, which will be E of ZT, right, times this. Is that okay? And so first of all, you see the importance of ZT being positive, right? Which is true with this exponential. Because if it's not positive, then you get a probability being negative, which is nonsense. On the other hand, right, this just guarantees that if I use A to be the omega event, right, then this is still 1, right? So it preserves the sensibleness of probability on the tilde side. Okay, so that's to explain these two conditions. On the other hand, right, what is this actual number? Well, you know, I'm not so sure because actually the calculation is not that straightforward, right? I mean, I could do it, but I think there are better things to do. So basically you have to do the integral, right? From 0 to infinity, right? Of e to the minus sigma square root of tx, right? 1 over square root of 2 pi e to the minus x squared over 2 dx, right? Whatever that is. That will be the answer to this. Square of big T, right? Do you agree? But whatever it is, it's not 1/2, right? Which is the probability of the original probability. Does that make sense? Do we understand what change of measure means? Let me give you another example. WT, right? What is expectation? Sorry, let's not take WT because it's a little bit awkward. What's expectation of E to WT? E to a sigma WT in the original probability.
Over sigma squared, T squared divided by 2.
Not T squared, just T,
Oh, just
because variance is T, right? Not T squared. All right. Now, what is E tilde of this guy? Well, it will be, in this case, very easy. Yes. So it will be all right. So is WT a Brownian motion under E tilde? Is WT a Brownian motion under E tilde? No, because otherwise it must be this answer, right? This is the moment gen function of a normal. It's not even normal, right? I mean, it could be normal, but could it be normal? It could, yeah, actually it still stays normal, right? But it's not this, right? Because the Brown motion will require this, all right? So you see that change of measure basically changed the distribution of all the things we know before. But which is a good thing because, right, our goal is not to show that WT is Brown motion in the P tilde, because that's no point. The point is the Brown motion would drift, right? This guy is the Brown motion under the new measure. And that's what we need to show next. All right. And probably this is a good place to stop. Okay, so we'll continue with this next time. Yeah, thank you.